Hi, today I will show you how to get beautiful sensor readings like this, and by the end of this video we'll even measure exactly how many microseconds it takes to acquire the data. Take a guess in the comments if you like. So we are building our sensor library for the MT6835 magnetic encoder. This encoder offers a very high resolution of 21 bits, which is perfect for us.
I even designed my own PCB for this project and got it from PCBWay for a good price. If you need high quality PCBs, 3D prints, CNC parts, or even sheet metal fabrication, PCBWay is your go-to. They offer fast turnaround times, affordable prices, and their online quoting system makes ordering super easy. Whether you're a hobbyist or a pro, PCBWay helps bring your ideas to life. Check them out using the link in my description below. Big thanks to PCBWay for providing these PCBs and for sponsoring this video.
Our library will let us read the absolute angle via SPI and the incremental angle via quadrature interface. This is how the code will look like at the end. The first thing we have to do is to include our header file for the tensor library, and then we only have to create an object in our sensor class, right? After we did this in our setup function, we only have to initialize our encoder or our sensor, and that's it. After that, we can just read out our angles via the function read absolute angle and the function read incremental angle. Okay, now that we know how our library will work, we can start by writing our header file. You can call it as you like. I just called it mt6835.h, but you can call it however you like. So, to make sure that our header file and the things we declare only be declared once, have to insert a command called pragma once. And after that, we have to include two more libraries. First, the SPI library, and second, the encoder library for our SPI interface and our quadrature encoder interface. So, type include encoder and include SPI. And now we can start to define our class. I will just call it like my header file. And in this class, we will now define a public section. So we can use those things that we write in it. Okay. The first thing I will do is to define a constructor. And this constructor lets me define an object later. Okay. So for our object that we used in our main file, I had 4 parameters, and those I have to define here, okay? The first one is the chip select pin. The second parameter is the SPI frequency. The third one is our A pin for our quadrature interface. And the last one is our B pin for the same interface. Now we can start to declare our functions that we will use in our main file. So we have our initialize function. We have our read absolute angle function. And we have our read incremental angle function. Just note that I typed here void because this function doesn't return anything, okay? And the other two functions should return data, so that's why I wrote float. Okay, since there are things we don't want to use or change outside of our class, we will define a private section. And in this private section, we have a few things we will declare. First, our SPI settings. Okay, and for that, I will declare a pointer for my SPI interface. I will tell you later why I did that, but you will see and understand. After that, I will declare the chip select pin parameter. The same goes for our SPI frequency and our SPI settings, which I will set later. Okay, great. Now there are a few more things we need to do. First, our SPI commands and registers. Then we need a few things for our absolute angle parameters. And then we need a few things for incremental angle parameters. Okay, and that's basically it. We need to fill those sections, of course, and I will show you now how to do it. Okay, I've opened now the datasheet, and you can see now the datasheet and the code, so I hope it's easier to understand what I'm doing and why. Right now I'm in the SPI interface section, and you can see here a standard single byte SPI angle read. This is one way to read the absolute angle of our encoder, but there's another way which works faster and this is called the burst read mode, and we will use that. But to understand what we are doing, there are a few things we need to talk about first. Our angle
consists
of 21 bits, and these 21 bits are saved in the register addresses 3, 4, and 5. Okay, so in this mode here, you would have to read every register on its own. Okay, in the burst read mode, you don't have to do that. You have one cycle and you just have to send the burst read command and the starting address. And after that, all registers for our angle will be transferred continuously. Okay, so this is what we will be doing.
But first we will do something else. To estimate how long a burst mode transaction will take, we will use the datasheet to calculate the data acquisition time and compare it to the single byte read mode. You can see here that one transaction takes 6 bytes. In the datasheet we can see that our clock period has to be at least 60 nanoseconds. That means our SPI frequency can be up to around 16 MHz. Since we are using 15 MHz as our SPI frequency, our clock period is around 66 nanoseconds. In total, we have to transmit 48 bits. That means our data acquisition time will be 48 bits times 66 nanoseconds plus TL plus TH. In total, we would accept a data acquisition time of 3.3 microseconds. At the end of this video, you will see if this estimation is right, so keep watching. Now we can do the same for the single byte read mode. Since we have 4 cycles with 24 bits each, our data acquisition time will be around 6.8 microseconds, which is more than double the time we need for our burst read mode. Okay, so let's get back to the code.
Since we want to use SPI, we have to declare our commands for our SPI interface, and you can see them here in the table. The most important is the read operation, the write operation, and of course our burst angle read operation. Okay, this is our burst command. It's an 8-bit number. In our case, I defined it with only 4 bits. So if you would look at it, it would look like this. Okay. Now we can declare the other 2 commands. Okay, these are our 3 commands we will use to send or receive data via our SPI protocol. Since we want to use the burst angle read mode, we only have to define our first or most significant byte register for our angle. So I type angle register most significant byte, address 0x003. Perfect. Now you can already see here on the bottom of our page how to calculate the angle in degrees. Okay, we want to use radians. That's why we need to declare a few more parameters so we can use our raw data to calculate it in radians. Okay, so the first thing we will do is to declare our resolution or our counts per revolution. Okay. So what did I do here? I declared a parameter, a constant, called counts per revolution. Counts per revolution maybe sounds weird, but the only thing that means is that we have 21 bit counts per revolution. So you could think of this as the smallest step our sensor can read, okay? I called it counts, you can call it step or whatever. And here you can see I took the number 1 and shifted it 21 bits. What this does is that it calculates 2 to the power of 21, okay? So it's just written here in a nice and easy way. Okay, and now since we want to calculate and get our angle reading in radians, we need to map those counts in 1 revolution over 2 pi, okay? Okay, so I declared a constant called rad per LSB. So this is our least significant bit. So I get the factor I need that you can see here to the power of 21 times 2 pi. So I have my angle reading in radian. Okay, now we can talk about our quadrature interface and the parameters we need for that, okay? The most important thing is the ABZ resolution registers, okay? We have register 7 and register 8 for that. And here we can set our ABZ resolution, yeah? As you can see, it has up to 16 bits of resolution, so it's not as good as our absolute angle, but it's just fine. So what we have to do now is to define those 2 registers because we want to use them in our class so we can set and also read our resolution for our quadrature interface. I called this parameter ABZ resolution register most significant byte. And the other register is the least significant byte. So now we can talk about a few things regarding our incremental angle parameters. The first thing we will have to do is we will have to define our encoder class or our object in our encoder class. Therefore, we call our encoder class and I will define an object that is called quadrature. Okay. Since it's a little bit tricky to calculate the incremental angle, we need a little bit help from a few constants. So we define them right now. Last ticks. Incremental angle, this is what we will get at the end. Okay, so we are just defining it right now. And now, before we talk about the other parameters, there are 2 very important functions we need. Okay, the first one is our function that sets our resolution. This looks a little bit weird maybe, but I will explain everything, okay? So we have here a function that has 3 input parameters. First is ABC on, second one is swap direction, and third one is our resolution. If you look back into the registers 7 and 8, you will see that 7 only consists of our ABZ resolution, the highest 8 bits, and register 8 consists of the lowest 6 bits of our register resolution, and the bit 1 is our ABC off, and our bit 0 is our AB swap, okay? So with bit 1, you turn our interface on or off, and with bit 0, you swap the directions of rotation, okay? And these are things, of course, we need to consider in our library because maybe the direction could be wrong, okay? And of course, we want the interface to be on always. The next function we need to declare is, of course, we want to print our resolution, so we declare a function that does that. And this function is called getABZ resolution. After that, we can define the remaining parameters. And this will be our resolution value. As you can see here on the bottom of our page, the resolution is a 14-bit word or I don't know, number. And the highest possible number in our case represents 16 bits. And of course, we want to use 16 bits, yeah? So we type 0x3FFF, and that's basically our counts per revolution or pulse per evolution, okay? We save this or declare this as a 16-bit number, but we need to keep in mind that these are only the lowest 14-bit, but you will see later what I mean by that. Now we can define our ticks per revolution. Since we use a quadrature interface, those ticks per revolution are 4 times this value here, okay? Now you may wonder why I typed here +1. This is because if you look at this number in our decimal number system, you will see that this is not exactly 16,384, but 16,383, okay? And this is why I have to add 1, okay? And then since we are using a quadrature interface, we multiply it by 4. And the last thing we need to do is, since we want to get our incremental angle, we need to calculate it in radian, just like we did before. So we map it over 2 pi. Okay, and that's basically it. We now defined our whole class and all parameters we need. And now we can start writing our code. Okay, so now that we finished our header file, we can start to write our CPP file for our library. The first thing we need to do is, of course, to include our header file. So we type include and then our header file. And if you remember, a few moments ago, I defined this funny thing here. This is a pointer to my SPI interface, okay? And I told you I will explain later why, and I will explain now. Later is now. I am using a TNZ 4.0, which has multiple SPI interfaces. So each interface has a different chip select pin, and chip select pin is a parameter in my class or in my object for my class, okay? So depending on which chip select pin I use, I have to use a different SPI interface in my code. And I don't want to always change the code depending on my chip select pin. That's why I have to use my pointer so I can set the right interface for my given chip select pin, okay? So it's all done automatically. I don't have to change my code depending on my chip select pin. What we do is we take our SPI class, which we have included here in our header file, and we use the pointer and create a function, okay? So we call it select SPI, and the input in this function is our chip select pin, okay? That we type in our object later in our code, okay? In this function, we will ask which chip select pin we are using, and depending on this chip select pin, we will choose a different SPI interface, okay? So if we are using chip select pin 0, yeah, then we want to use our SPI interface 1. If we use chip select pin 10, yeah, then we want to use our SPI interface. Yeah, it doesn't have a number. This is the default SPI interface. Okay, and if we use chip select pin 36, then we want to use our SPI interface 2, okay? If I put in a number here that doesn't fit to our chip select pins, then I will just return our default SPI interface, okay? That's basically it. That's why I used my pointer. Okay, now that we finished this part, we can start writing our sensor object, okay? Okay, what we have here is our object that is part of our class that we defined before. And these are our 4 input parameters we've talked about earlier, okay? And those parameters need to be initialized. So we type the following code. Okay, so what we did here is that I initialized all my parameters with the input I am giving this function. So we have our chip select pin, our SPI frequency, and we have our SPI settings. And these settings are set on base of the datasheet, okay? If you read the datasheet, you will see the byte order is most significant byte first, and we use the SPI mode 3. Then we initialize our quadrature object from our encoder class, and we set our angle readings for the incremental angle 0. The last thing we need to do is to set our SPI interface before we start, okay? And this is on basis of our chip select pin, as I explained before. Now we can talk about the read absolute angle function. As you can see here in the datasheet, and as I explained before, you have to send the burst command and the start address. After that, you get the 4 remaining addresses, 3, 4, 5, 6, that contain the data of the angle, okay? And this is done continuously until you toggle the chip select pin again. So what we have to do in this function is we have to declare a data array which consists of 0, and this is because we need these 4 register bytes to be 0, because these are dummy bytes and we want to get the data, okay? The first byte in our array will be our command. Since our command contains only 4 bits, we need to shift it to the left, and this then will be our burst command. The second byte of our array will be our start register, in this case our register 3, which we have defined earlier, okay? If we did this, we can start our SPI transactions with the SPI settings we declared before. We have to toggle our chip select pin, then we can transfer our array, and after that we have to toggle our chip select pin again, and we can end our transaction. When we did that, we can calculate our angle, and we do this by combining the addresses 3, 4, and 5 together. Since we have 21 bit, we need to shift our most significant byte, our register 3, 13 bits to the left. Our register 4 data needs to be shifted 5 bits to the left, and the data from register 5 needs to be shifted 3 bits to the right, since we don't need every single bit in this register. And then we multiply it by this constant I defined before or declared before, so we get the angle in radian. You could also check the status and the other parameter, but in our case this is not interesting, but if you want to do that, you can do it here. The incremental angle reading is a little bit interesting because, of course, we don't use our SPI interface, but our quadrature interface, okay? So what do? We count our ticks, yeah? Or we read our tick count, and then we calculate the difference between our ticks that we made and the ticks we had in the previous time step, okay? Then we override our last ticks with the current ticks, because this is a operation that goes continuously, so we need to override the last ticks with the actual current ticks. And if we done that, we can use the difference and calculate by the tick angle, which is basically like our least significant bit. And then we just have to add those numbers up, and this gives us our incremental angle. That is what we return in this function. Now it will be a little bit more complicated because we will talk about the ABZ resolution. So we have our set ABZ resolution function, which we have declared before, and this function has 3 inputs. And one input defines whether the interface is on or off. The other one defines the spinning or counting direction, and the third one defines the resolution we want to set. So what we have to do is we first have to write our register 7, and then we have to write our register 8 over SPI. And as you can see here, our resolution is only a 14-bit word, which will be mapped on register 7 and on register 8, but not completely on register 8, because bit 1 of register 8 will determine whether the interface is on or off, and bit 0 defines the counting direction. What we need to do is first to write our register 7 with this following word. Okay, so what we do here is we take our wanted resolution, in this case 0x3FFF, which is a hexadecimal number, and we shift this number 6-bit to the left. Okay, we do that because this value, IBZ resolution value, is saved as a 16-bit word. Okay, so these 16 bits need to be shifted 6 bits to the right, and by doing that we can now take only the lowest 8-bit, and by doing so we get the highest 8-bit of our value for our resolution. I know it sounds a little bit complicated. Our number 0x3FFF is this number here in binary. So 001. This is our number in binary. Okay, now we shift the whole number 6 bytes to the left. So we have, if I didn't do anything right, we should have this number. And now if we take the lowest 8-bit of this number, we would have only those 8 bits. And as you can see, those 8 bits are or if you think about it, or if you think about it, the highest 8 bits of our resolution. Okay, so this is a good way to do this, right? And now after we wrote register 7, we can write register 8. So we do the same, we send the write command and the register we want to write. And now it's a little bit more complicated because we also need to set bit 1 and bit 0 of register 8. Okay, so what do? We take our resolution value and we only use the lowest 6 bits. Okay, and those lowest 6 bits are shifted 2 bits to the left. I will also explain here why we do that. So here is our number again that defines our resolution. Okay, and what we do now is we take the lowest 6 bits. So this number here, 0x3f, is nothing else than this number in binary. Okay, the lowest 6 bits. Now the AND operation takes this number and this number, or basically, since we are using 16 bits, basically this number, it's just the same as here. And on every bit where you have a 1 here and a 1 here, these bits will remain. So if I do that, I will be left with only this number. Okay, right? So let's go one more back. I will remain with only those 6-bit at the bottom. Okay, so this is basically what we want, right? But since we have here in our register 8 bit 0 and bit 1 as different bit functions, we need to shift those 6 bits 2 bits to the left to make place for turning the interface on or off and defining the counting rotation. So what we be left here is those 8 bits, where the highest 6 bits are our IBZ resolution bits 5 to 0, okay? And the lowest 2 bits are our swap direction and IBZ on bits, okay? We have here our lowest 6 bits, and now we combine them with the lowest 2 bits, right? So the lowest 2 bits are defined in a way that we ask whether is ABZ on true or not. And if it's true, then bit 1 here in our register 8 is 0. If not, it's 1. Since it's bit 1 and not bit 0, we need to shift this single bit 1 to the left, okay? And the same principle applies to swap direction. We ask whether swap direction is true. If yes, its number or its bit is true, so 1, and if not, we insert a 0. By doing that, we can turn on or off the interface and swap the direction. The resolution is not touched by that. Okay, and that's basically it. Okay, now that we finished writing our library, we can test it, okay? So I will upload my code, and I will take my motor, and now I will start the serial interface. And you can see here, the resolution is set as we wanted it to be. And now, if I open the plotter I'm using, then you will see a nice reading of my sensor data. I love it. And now, as I promised, I will also show you how long it takes for the Teensy to calculate the sensor reading. And you can see that my incremental encoder, or the incremental angle, only takes 0.057 microseconds or 34 MCU cycles to calculate the data. So the reading you can see here for my absolute angle is almost as we calculated earlier, so it's not that far away. So I think it's a satisfying result. I am happy with it. Thank you for watching this video, and I hope you learned a little bit, and maybe you will also implement an own sensor library after watching this video.